recording the session. And if someone can confirm that you can hear me. There we go. Mr. Naika says, please can you do 38 of chapter 11.3. Okay, let's have a look at that. Let's have a look at that. I'm just opening everything up again. You'll need to give me a minute or so. Okay, find, okay, I've got it, estimate the sum, find the sum of the series. Okay, let us share the screen and everyone can see. There, you should be able to see it now. I'm going to show this and then we'll see if we can go to the lecture and look at the relevant theory, because I want to always point out to you how the theory connects to what we do. So there's number 38. It says, find the sum of the series, the sum from 1 to n, from 1 to infinity of n e to the minus 2n, correct to 4 decimal places. Find the sum of the series correct to 4 decimal places. I think we may actually need some of the material we haven't covered yet. Lecture 2 slides, lecture 1 slide, lecture 3 slides. Okay. So I'm going to show you what we need and explain to you what to do, and then maybe we can look at it next week, because we do need to do the material on estimating sums first. So we ended up our lecture on Tuesday with the end of example 2. So before we continue, I'm going to remind you of the integral test, and then I'll show you the bit that we still need to be able, that you still need to do this problem. So you are a little bit ahead, Mr. Naika. So there's the integral test. The integral test says, suppose that f is a continuous, positive, decreasing function on the interval 1 infinity, or on the interval consisting of the set of numbers larger than or equal to 1, and let a n be equal to f of n. Then the series, the sum from 1 to infinity of a n, is convergent if and only if the improper integral is convergent, the integral from 1 to infinity of f of x, which means if the integral is convergent, then the series is convergent. If the integral is divergent, then the series is divergent. So the important thing is to notice what the conditions are for being able to use the integral test. F must be continuous, positive, and decreasing, right? Now, notice that this function f is defined for all real numbers, whereas the sequence a(n) is defined only at values that are positive integers. In other words, 1, 2, 3, 4, and so on. But it's always the case that a(n) is the value of that function which is continuous on the entire interval 1 infinity, the value of that function at n. So that's the important thing, right? So now let's go back to your question. So there, 38. Find the sum of that series correct to 4 decimal places. Okay. So the first thing you need to see is that in order for us to apply this integral test, we need to come up with a function that's continuous on that interval starting at 1 and for all numbers, for all real numbers larger than or equal to 1. And that function must have the property that at particular natural number, at each of the natural numbers, the value of that function must be the same as the value of this sequence that generates the series. In other words, we need to look at a function, the function. So I'm going to share my screen. I'm going to see if I can write now, because I do want to test this writing solution so that we can use it in future. Okay, so I'm going to switch to, I think I'm going to switch to a different application. So I'm going to have to stop sharing, then start sharing again. And we see how the writing goes. Okay, so I've stopped sharing. I'll look at the chat quickly. Okay, there's some more stuff happening. Okay, we stay with 38 for Mr. Naika, and then when we're done, we'll go again. Okay, so now I'm going to share screen again, and this time I'm going to share the writing pad. So let's see how this goes. Okay, so now let's see how this works. So now we've got the series. The thing that we're looking at is the series of n. Now I need to go and check again. Of n e to the 2n, e to the minus 2n, n e to the minus 2n, right? And this is n going from 1 to infinity. We want to discuss the convergence or divergence of this series. Now, remember what the theorem says. The theorem says this, we need, in order to use the integral test, we need to define a function which is continuous, right, and decreasing. Okay, so you'll have to forgive my, it must be continuous starting at 1. And I'm thinking, I'm getting lots coming in. Maybe you can't see again. Let's see. Share, screen not shared. Let's try it again. I'm sharing the screen again. We'll talk about WhatsApp modules in a minute, or WhatsApp groups. So there is 2, 3, and so on. Right, now, the theorem says, the integral test says, we need to define a function f of x with a property that it's continuous and decreasing. It's continuous on the interval 1, infinity, and it's decreasing. So it has to do something like that. Remember what continuity meant. It meant it didn't have any sharp jumps or step discontinuities or anything like that. I should be able to draw the graph without lifting the pen off the paper. And this function must also have the property that at these particular values of the real line, in other words, all the natural numbers, the value of the function must be the same as the value of the sequence that generates the series, right? For n equals 3 in this case. Let's fix that quickly. So in this case, I must have 3e to the minus 2 times 3, and so on. So that means I need to define this f of x to be equal to x e to the minus 2x, if you think about it. Because this function, the function that we use, the function for which we calculate that improper integral, that integral from 1 to infinity of f of x dx, that function must be defined for all real numbers larger than 1. And so if I define f of x to be this function, then automatically at each of the natural number values of the real line larger than 1, well, they all are larger than or equal to 1, for all the natural numbers, the value of the function will coincide with the value of the sequence. Got it? Now we've got the setup for the theorem. Now we need to do a few things. We need to first double check that the conditions for this theorem are satisfied. In other words, this function has to be continuous. Well, it is, because the function h of x equals x and the function g of x equals e to the minus 2x. These are both continuous functions, and we know that if we multiply two continuous functions, then we get again a continuous function, right? And so we know that this function is continuous using the material we covered in the 1a module. So we know that this is a continuous function. Now we need to make sure that this is a decreasing function, right? So here's where I'm going to point at things you need to do as part of your solution, Mr. Naiker, and then leave it over to you. You need to now prove that this is a decreasing function. Now I'll remind you that a function is decreasing if its derivative on an interval, if what's the first derivative test, right? If the gradient is going to be negative, if I pick any 2 points. And so for this one, I'm going to have to calculate f, or one way to do it is to calculate the first derivative of x, first derivative of f, and show that this is a decreasing function using one of the tests we did in the 1a module. So now you've got that it's continuous and it's decreasing, right? What are the other conditions in the integral test? You need to show that they're all satisfied. Now I'm going to go back to the slide for the lectures for this week and show you the material that we will cover in tomorrow's lecture, after which you will have, you're obviously free to read ahead, but after which you will have enough material to be able to complete the problem. So I'm going to stop sharing again, go look at the comments for a second, and then share again. Okay, so I've stopped sharing. I'm going to share again. Ramatsetse, I will look at your question in a minute. I will allow you to ask your question in a minute. I just want to finish answering the question from Mr. Naika. So there's the integral test. There is the proof. There is example 1, example 2 we completed. We'll pick up tomorrow evening's lecture with example 3, and then example 4, and then we will do this section, which is a subsection of 11.3. It's called estimating the sum of a series. As you can see, I haven't put in the pauses yet, so I do the pauses just before the lecture to see where to stop and start the material that you see, so that you can see it moving. Okay, so basically, estimating the sum of a series allows us to set up an upper and a lower bound for the sum of a series. So we'll be able to say, for this particular series, we don't know what its exact value is, but we can estimate the value of that sum to within 1 in 1,000. In other words, whatever the estimate is, the true value is either the estimate plus 1 in 1,000 or minus 1 in 1,000. Okay, and so there is an example 5 that shows you approximate the sum of the series by using the sum of the first 10 terms, estimate the error. How many terms do we need? And this is what you need to continue to tackle that problem. You're free to read ahead for tomorrow's lecture, or to wait until the lecture and then to tackle the problem. I'm going to stop sharing. Then we look at another question. Okay, Mr. Wu says, is our semester test 1 scope? 38, that was Naika, 38. Mr. Naika and Ms. Opperman chatting about something. Mr. Wu, is the scope, is our semester test 1 scope at least? Yes, it's going to be 1.1, 11.1 to about 11.8 or 11.7. I'm not quite sure yet. I think we do 11.8 a day or two before your semester test. So I'm tempted to stop at 11.7. Okay. Is there a WhatsApp group for this module? No, there isn't a WhatsApp group, but I will post the email details for the tutors later today. The tutors have now been added onto Blackboard. The tutors are added on WebWork. And so I've told the tutors that it is up to them whether they want to communicate with you as students using WhatsApp, right? So I will post in an announcement today, and I'll update the study guide with the email addresses of the tutors. If you want to communicate with a particular tutor via WhatsApp, then send that tutor, that person, an email and ask him for their number. Okay. Okay, so there was a question about, can I have a hint? Okay, that's between. Okay, cool. So that's actually all the current questions sorted. Okay, Malobola, section 11.2, exercise 11.3 exercise 46. Okay, let me find it quickly. 11.3 46. Also, I'm going to see if the tutors can alternate with me in taking the tutorial session. 11.3. Okay, 11.3. I'm battling to find that. Just give me a second. 11.346. I'm going to share. Okay, Ms. Opperman says, when will we start having video lectures instead of live lectures? When we have to watch the videos for the lectures, will we still have the live tutorial sessions? I'm going to see if I can record tomorrow evening's lecture, today or tomorrow, and post it beforehand. Just to make sure that there's a smooth transition, we will see if we can, I will see if I can do both the lecture and the tutorial, the lecture and the recorded video tomorrow evening. Once everything works, we'll do recorded lectures. And then to answer your second question, will we still have these live tutorial sessions? Yes, I'd like us to continue with the live tutorial sessions. And what I'd like to do is, if one or more of the tutors can do similar online collaborate sessions, then we can actually do more than one in this double period on a Wednesday. Okay, now I'm going to focus on seeing that question. Okay, 11.3, almost there. Okay, 11.346. I'm going to share it, and then we'll see how we tackle it. Okay, so there you should see it now. Find all values of C for which the following series converges. So it's C divided by N minus 1 divided by N plus 1. And that's the series. So it's the sum from 1 to infinity of Cn minus 1 divided by N plus 1. Okay? So now, if we had a C on the second, in the second term, we could factor out the C. But we don't. So we only have the C in the first term. So something we could try to do is to see if there's some kind of pattern that comes up. Similar to the cascading pattern that we saw in one of the examples. So let me make a note of what the question looks like, then I'll share my screen and we'll see how to approach this. So that's the sum, n equals 1 to infinity, C divided by N minus 1 divided by N plus 1. Good. So let's see. So now I'm going to stop sharing for a second and then share again. The writing pad. Okay. So let's start a new page. Let's start a new page. There's a new page. We are going to say the question is find all values of C such that the sum n equals 1 to infinity of C divided by N minus 1 divided by N plus 1 converges. Okay. So let's calculate the sum for a few values of n. So remember the partial sum, the sum up to n terms, is given the symbol S. And that is the sum, and now we need to change the index because we need n for the final term, I from 1 to n, of C divided by I minus 1 divided by I plus 1. So let's see what happens if we calculate this for a few values of n. So if n is equal to 2, say, so what we're trying to do is to look at some patterns to see if we can see a pattern emerging. So S2 will be the sum I from 1 to 2 of C divided by I minus 1 divided by I plus 1. And this is equal to, when I is 1, I get C divided by 1 minus 1 divided by 2. Right? And then I need to add plus C divided by 2 minus 1 divided by 3. Okay. And I'm going to say, I'm going to reorganize things and put the C's together. and put the numbers together, because it's, for me, it seems like the next natural thing to try. So C1, C divided by 1 plus C divided by 2. Now those are negative. Half is negative and the third is negative. So I'm going to say negative in bracket 1 over 2 plus 1 over 3. Okay. Now let's try n equals 3. N equals 3 will be S3 equals the sum I from 1 to 3 C divided by I minus 1 divided by I plus 1 is equal to, and it's going to be C divided by 1, yes, minus a half. Yes, because when I is 1, that second term still gives me a half. Plus C divided by 2 minus a third. Okay, so that stays the same. Plus, now it's going to be, the next one's going to be C divided by 3 minus 1 over 4. We can see the pattern already. So this is going to be C plus C divided by 2 plus C divided by 3, right, plus minus half plus a third plus a quarter. And now both of these should start reminding you of the harmonic series, right? Because the second one here, or the first one, so this is going to be C, and I can factor out to C here, and I get C1 plus a half plus a third minus 1, a half plus a third plus a quarter. Nice. Okay, so I'm beginning to see a pattern emerge here. So let's do it. Let's see if we can do it for Sn. So S, the partial sum up to n terms. This is going to be the sum I equals 1 to n of C divided by I minus 1 divided by I plus 1. And this is going to be equal to, okay? So we know the first term is going to be C divided by 1 minus a half. We know the second term is going to be C divided by 2 minus a third. Plus, now we can't write out all the terms, so we put down dot, 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 that we can see the pattern, and then the last term is going to be what? Okay, so for the last term, the value of I is n, so I'm going to have C divided by n minus 1 divided by n plus 1. Okay, and this is going to be equal to, well, I can split them again, the same way as I split them here, and I'll get C into 1 plus a half plus a third and so on, right? So it's going to be 1 plus a half plus a third plus 1 over n, right? Right. Plus, now in this one I'm going to have, starting at the half, actually no, this is wrong. This bit is wrong. I'm going to have minus. Now I'm going to have a half plus a third plus. The last term is going to be 1 over n plus 1. Okay. So now we need to somehow rewrite these two terms so that we can see either that the thing converges or diverges, right? So remember, we want to know which values of C allows it to converge. So what I'm going to try and do is I'm going to try and get rid of this 1 so that this part together with a C, so that this part of the first bracket together with a C looks like this bracket here. Okay, so I'm going to say this is C, the C times 1, plus C times a half, plus a third, plus 1 divided by n, minus I'm going to say 1 divided by n, and the last one I'm going to leave alone, minus 1 divided by n plus 1. We'll see if that gives us a pattern in a minute. Let's scroll. Okay, so now I've got C plus C, and what I've got there in both cases is C times the harmonic series minus the harmonic series, right? So I'm keeping that in mind. So somehow this is going to be related to the harmonic series. Okay, so how can we, what's the next step now? Okay, is there a different way of combining them? Is there a different way of combining them? Let's look at this again. Let's start with this expression again and see if we've got a different way of combining them. Okay, so Sn is the sum I from 1 to n C divided by I. Okay, so it's 11:15. So you are welcome to leave the session if you need to go somewhere else, but you're also welcome to stay. I can stay for a little longer. Right. So this is going to be C divided by 1 minus a half. Let's rewrite it again and see if we can rearrange the terms differently. Let's add another term. So the next one's going to be C divided by 3 minus a quarter plus C divided by n minus 1 divided by n plus 1. Okay, now notice that I can write the same thing now, but move the brackets. So I'm going to remove this one, then move the brackets between these two, which are fractions of 2. Okay, so it's going to be c divided by 1, and then plus bracket minus a half plus c divided by 2 plus bracket minus a third plus c divided by 3. So what I'm going to try and do now is to move them. These two terms are similar because they've got the same denominator. And this is what I'm doing all the way through. Plus, there's going to be minus a quarter plus c divided by 4 plus, and so on. Right? And so this is going to give me c divided by 1 plus c minus 1 divided by 2 plus c minus 1 divided by 3 plus c minus 4 divided by 4 plus. Now what will the last one be? The last one will be c minus 1 divided by n. And then there'll be this term remaining. So c minus, sorry, that should be a 1. This must be c minus 1 divided by 4, c minus 1 divided by n. And then the last term is going to be minus 1 divided by n plus 1. Okay, so now what does this allow us to do? So we've got c plus c minus 1 over 2 plus c minus 1 over 3 plus c minus 1 over n, and that last one has a negative sign. So now we can rewrite this as, we can factor out the c minus 1 from all of these, and we can get c plus c minus 1 times, again, something that looks like the harmonic series. 1 over 2 plus 1 over 3 plus, in the end, 1 over n. Right? Minus 1 over n plus 1. Right, and now let's see if we can calculate the limit. So we've got this expression now. We can say the limit as n goes to infinity of Sn, remember that's the sum, is going to be the limit as n goes to infinity of the right-hand side here, right, which is the limit of c plus c minus 1 times the sum I from 1 to n 1 over I minus 1 over n minus 1. Okay? And now we can say this series here, right, is the harmonic series, and it will diverge. This is basically n plus 1. This must be n plus 1. So this bit here that I've underlined is the harmonic series. And that will diverge. And if it diverges, then any constant multiple of a divergent series will also diverge, right? And so this last limit exists if and only if this bit goes to 0. So that limit exists if and only if C minus 1 times that sum, 1 over I from 1 to n, that limit exists if and only if C minus 1 is 0, if and only if C equals 1. Okay, so that's definitely one that takes quite a bit of thinking and quite a bit of work. Okay, we are quite far into over time, so I'm going to stop sharing. We'll have a quick look at chats. Any last questions? No, there's still 9 of you left. Okay, so that ends the tutorial for today. We will continue with the lecture tomorrow evening. As I promised, as I'm planning to, I'll see if I can record the lecture beforehand, post the video. I'll still have the lecture just to make sure that there's a smooth transition. Once the recording of the lectures works, I'm going to more often do recorded lectures and post them. I think the file size is a lot smaller than the ones that we have on Collaborate anyway. So see you tomorrow evening at 6. Okay, thanks for coming. Cheers.